Hey everybody, welcome to chapter 14. We're going to be talking about probably my favorite or one of my favorite statistical analyses and one of the most useful and commonly used in psychology, which is the independent samples t-test. Let's dive in. Let's get some quick review. So when do you use a single sample t-test or a one sample t-test? This is going to be C. If you've collected numeric sample data and you want to compare it to numeric population data, that is a single sample t-test as long as you don't know what the population standard deviation is. If you know what the population standard deviation is, you could actually use a one sample z-test. In this chapter, we're going to continue with this example research question about whether psychics are actually more accurate than non-psychics in correctly predicting card suits. In the chapter on one sample t-test, we were comparing the mean correct accuracy, I guess you could call it, of guesses from psychics to a previously established population mean. But in this chapter, we're actually going to be comparing two different samples. So it's not comparing one sample to a previously established population. We're actually going to be comparing means from two different samples that we gather from populations. So as the figure is showing you, we're going to have two different populations. We're going to have a population of psychics or self-described psychics and a population of non-psychics. We're going to get a sample of each of those, 50 people from each of those populations, and that's going to give us the sample mean and sample variability or sample standard deviation and variance for each of those populations. And we need those things to eventually calculate what's known as pooled variance and then estimated standard error so we can find our t-score from there. So again, we're getting two separate and independent samples. We're going to have to go to two different groups of people and recruit samples from these two different groups of people. Each of those samples is going to give us its own mean and standard deviation, and then what we're asking is, based on the means and standard deviations of these two samples, are they actually significantly different from one another? Are the two sample means of card prediction accuracy significantly different from one another? And of course, when we set up our hypotheses, we can actually set this up in a directional way using a one-tailed hypothesis and one-tailed t-test, or we can set it up in a non-directional way and use a two-tailed hypothesis and a two-tailed significance test or t-test. So when you have two separate and independent samples, meaning the scores from one sample have nothing to do with and cannot affect the scores from the other sample, this is called a between subjects design. We saw within subjects design in the chapter on dependent or paired subjects t-test. Now we've got between subjects designs with independent samples. And the thing is, there's still two flavors of this. You can actually draw samples, two samples from two different populations, one sample from each of those different populations, or you could actually grab one large sample from one population and then distribute those people randomly assign them to two different conditions and then compare between the conditions. So these diagrams kind of speak to those two different flavors of between subjects designs. In the top one, again, you have two different populations and you're recruiting a sample from each of those populations that you'll then compare their means of, in this case, it's card prediction accuracy. Or you can just get one sample and then split that one sample into two different groups and have them go through different conditions, different situations, different treatments, different experimental manipulations, and then compare between those. But basically, all this is saying that you never have one participant being involved in multiple treatments or multiple conditions like what we saw in the within subjects designs. These are all between subjects. So you only have them do one thing and compare that to other people who did something else. And also just want to make sure to get everybody on the same page about, well, what's the independent variable and the dependent variable when you're talking about independent samples t-tests, right? So let's take this example. We've got two different majors, psychology majors and business majors, and we're measuring those folks in terms of their happiness. And we want to compare the happiness of psychology majors on average to the happiness of business majors on average, right? So you actually have two different variables here. The independent variable, the X variable, is what major you are. And so the two different groups are psychology majors and business majors. So that independent variable of major has two levels, psychology or business, right? And what we're actually measuring, the dependent variable, is their happiness. So that is a numeric variable, and we are going to actually compare the happiness of psychology majors on average to the happiness of business majors on average. So whenever you're doing an independent samples t-test, the independent variable is whatever category the groups come from, and then the dependent variable is what you're actually measuring numerically. All right, so before we actually get into computing a independent samples t-test, we want to do a quick review of when do you use the different kinds of t-tests, because there's 3 different kinds of t-tests we've covered. All of them you're going to use when you do not know the population standard deviation sigma. We've covered a single sample t-test or a one sample t-test, and that's when you want to compare a single sample's mean on some variable to a population mean on that variable, right? The paired or related samples t-test is when you want to compare two different means from a single group, one sample. So basically you measure all of the same people in a sample 2 different times, and then you're going to measure basically the differences between those 2 means. In an independent samples t-test, which is what we're doing this chapter, that's when you want to compare 2 separate groups' means, 2 separate sample means. And those samples are of different people. When you're actually conducting the independent samples t-test, you're going to have to calculate, as we've always been doing, some kind of inferential test statistic. In this case, it's going to be a t-statistic, a t-value. And the way we calculate that here is different from previous tests we've talked about. We're going to actually take the mean differences observed between the samples or between the 2 conditions for independent people in those conditions. And we're going to subtract the, what you'll see in a minute is going to be the expected mean difference in the population, which is almost always 0. And we divide all of that by, again, the estimated standard error. That's been similar through the past couple of examples and past couple of chapters, but here we're going to calculate the estimated standard error, again, a bit differently. In previous chapters, we've always calculated the estimated standard error or the actual standard error with only one sample. And so this is kind of an interesting conundrum. How do we do it with 2 different samples? Well, aren't you in luck? I'm about to show you. So a quick review. If we're just looking at raw scores, this is just scores on some kind of measure, happiness or IQ or whatever it is, and you want to find the standard deviation of just a bunch of raw scores, first of all, you have to find the sample variance. And the variance is denoted by S squared. And the sample variance is equivalent to, do you remember what SS is? That's the sum of squares. That's when you take every raw score, subtract the mean, and then you square all of that. And so you have the sums of squares on top, and then you divide it by n minus 1 if you're talking about samples, because the n minus 1 is kind of a little corrective factor. Then, if you want to find the sample standard deviation from there, you actually take the square root of the sample variance, or taking the square root of that entire term on the right side of the equation. And why am I bringing up standard deviation and variance? Well, it turns out that in independent samples t-test, because you have 2 samples, you actually need to calculate something called pooled variance, which is just another way of basically calculating variability. But this time, it's variability when you combine two different samples, which we have not seen yet. And the way they do it is not using standard deviation, but actually using variance. So just trying to get you used to this idea, even though standard deviation and variance are immediately related, because you just square standard deviation to get variance, or you take the square root of variance to get standard deviation. These calculations work a lot easier if we use variance. So let's see what that looks like soon. Up to this point, we've been estimating standard error in the one sample t-test and paired sample t-test by just using the standard deviation of the sample over the square root of the sample size. You can also convert that type of estimated standard error formula into a variance form, and it just looks like on the bottom there. It's the square root now covers both the numerator and the denominator, but now the term is variance instead of standard deviation for the sample. But now that we have two samples in the independent samples t-test, we need to actually pool those variances or combine variances from two different samples. So the equation here is on the right. It's s squared, which is variance, and the subscript p, which indicates it's a pooled variance, is equal to the sums of squares from the first sample plus the sums of squares from the second sample, and you divide that by the total degrees of freedom, which is the degrees of freedom n-1 for the first sample plus degrees of freedom n-1 for the second sample. And again, this is conceptually the same as other estimates of standard error that we've seen previously this semester, in that it's a measure of variability. This time, though, it's based on variability of two samples instead of one. It is still an estimate of the sampling error, like how much our sample actually differs from what we would think it would be in the population. But the interesting thing about this is that it's a weighted measure of variability. So the degrees of freedom are directly proportional to sample size, right? Because they're sample size minus 1. What this is saying is that the pooled variance is going to be more similar to typically the larger sample, because it's weighted so that the larger samples actually contribute more of their variance to the overall pooled variance score. Because if you think about it, you don't actually have to have, and this is usually the case, you don't always get two samples of exactly the same size. If you're trying to recruit from two different populations, oftentimes you actually get samples that could be, many people different, like a sample of 100 people versus a sample of 70 people, or a sample of 1,000 people versus a sample of 523 people. This helps us kind of take care of those differences. And before we actually find out how to use pooled variance to calculate ultimately an actual t-score, we're going to talk about the hypothesis testing steps with an independent samples t-test. They're basically the same as we've already seen, just the calculations are going to differ a little bit. As always, step one is to state our hypotheses. So an alternative hypothesis we could use, this would be an example of a one-tailed hypothesis, would be the population mean accuracy for psychics will be higher than the mean accuracy for the population of non-psychics. And you can see the mathematical notation for that would be mu subscript psychics is going to be greater than mu for the non-psychics. We always talk about populations in our hypothesis, even though in practice we're usually taking samples. But what we're actually interested in as a scientific endeavor is thinking about populations, and we estimate characteristics of populations using samples. The null hypothesis, alternatively, well, I shouldn't say alternatively, that's confusing. The null hypothesis is, in contrast, the population mean accuracy for psychics will be lower than or equal to the mean accuracy for the population of non-psychics. Another way we can state this is in terms of the alternative hypothesis, the difference between condition means or sample means should be greater than 0 in these two populations. Think about that for a second. Because if we're, similarly to when we were talking about the dependent samples or paired samples t-test, we our idea is that these means should be significantly different from each other in the alternative hypothesis, which means that when you subtract one from the other one, they should be significantly different from zero, because if they were close to zero or basically the same as zero or equal to zero, then they're not very different numbers at all, and they're probably not significantly different. So an alternative hypothesis, if we think that the psychics will be better, will have much significantly higher accuracy, then if we subtract the mean accuracy of the non-psychics from the mean accuracy of the psychics, that number should be large, should be greater than zero. And of course, the null hypothesis in comparison is going to be the difference between condition means, or in this case, sample means, would be less than or equal to zero. And a quick note here, if it turns out, after we do our hypothesis testing and make a decision, that there is not a significant difference between the mean accuracy for these two populations, they in fact probably are not from two different populations in the beginning. It's like, yeah, we purposely sampled people who identify themselves as psychics and people who identify themselves as non-psychics, but ultimately, in reality, maybe those groups are the same because maybe nobody has any psychic powers at all, right? And so this is saying that if we see that the mean accuracy for both of the same groups, or both groups, is almost the same, and therefore the difference is zero or not significantly different from zero, then they probably actually don't come from different populations. So hopefully that makes sense. Step 2, set the decision criteria. As always, we set our alpha level, our significance level at 0.05. And I oftentimes like to try to look at the t-table or the unit normal table before actually getting to the calculation step. But in practice, right, like you need to collect the sample before you know how many people are in your sample, and the degrees of freedom or the number of subjects in your sample is really important to know for calculating those things. So I'm just going to leave that closer to the end this time. Okay, so step 3, actually time to collect our data. This is a little twist because in this example in your book, we actually get uneven sample sizes. So we're only able to recruit 45 psychics, but we are able to recruit 50 non-psychics. And we'll see how that plays out in the calculations in a second. Step 4, calculate statistics. You would want to use this chart to actually help you figure out which statistical analyses are appropriate even before you're collecting sample data. So like way in advance, while you're even just thinking about what kind of scientific study to do. But in this case, if we are comparing means versus testing relationships, we're comparing means. How many sample means are there? There's going to be 2. Is it a between subjects design or a within subjects design? It is a between subjects design, so we get ultimately down to the independent samples t-test. Let's actually conduct that test now. Now, in every single statistical analysis we've talked about this semester, we've had to calculate either the standard error or the estimated standard error before we can ultimately calculate, the inferential statistic of interest, whether it's a z statistic or a t statistic. This time the math gets a little bit more challenging because we are still going to calculate an estimated standard error using sample variance. Usually you do it using sample standard deviation, but we do variance here. But now there's 2 samples, right? So we've got to first of all, calculate the pooled variance of both of the samples, which let's just say we've got some data. We know that for the degrees of freedom, each of those samples is going to be n minus 1. And we saw in the previous slide, if we got 45 psychics and 50 non-psychics, then 45 minus 1 gives us 44, 50 minus 1 gives us 49, and that is going to be the degrees of freedom total on the bottom denominator of the pooled variance equation. And let's say that we found out that the sums of squares was 550 for psychics and 350 for non-psychics, and so you get a total pooled variance of 20.93. Well, now we still need to calculate the estimated standard error from that. Now we're using variance instead of sample variance instead of sample standard deviation, but it's pretty similar in practice. So the estimated standard error, which is S subscript x1 bar minus x2 bar equals this whole thing, the square root of the pooled variance over the number of people, the sample size for psychics, plus the pooled variance again, it's the same number, divided by the sample size of now your non-psychics. And so if you do work out all of that math, you end up with 0.94 as the estimated standard error. But we're not done yet. Of course, we have to actually calculate the t-statistic for the independent samples t-test, and it has a new formula, although it's sort of reminiscent maybe of the dependent samples t-test. Basically, we're going to take the mean of sample 1, x1 bar, minus the mean of sample 2, and subtract from that term the estimated population mean difference. That's mu1 minus mu2. Now, in all actuality, this is basically always going to be 0, because in the null hypothesis, we're expecting that the population differences will be 0. The mean population differences for each population will be 0 in the null hypothesis because we're expecting them not to differ at all. So if you subtract one from the other, they should equal 0. So basically that whole mu1 minus mu2 term just drops out of the equation because you're subtracting 0, and so nothing happens. So I've seen textbooks that don't even include that term in this total equation because, well, we're basically always comparing our sample mean differences to a population mean difference of 0. Anyways, we divide all of that top term, the numerator, by our estimated standard error that we already calculated. So what we end up with, let's say, and this is just, hypothetical data from the textbook, that we have a sample mean from psychics, which is x1 bar, of 26% accuracy, minus the sample mean from the non-psychics, which is 25. We divide that by 0.94, so we have 1 divided by 0.94, and we get 1.06 finally is our actual t-value that we're going to compare against some critical t-value. Now, in order to compare the t-value we just calculated to a critical t-value that would come from a table, or you could calculate it from an online calculator or something, we need to know the total degrees of freedom, which is just the degrees of freedom from our first sample plus the degrees of freedom from our second sample. You can think of this as degrees of freedom, sample size of sample 1 minus 1 plus sample size of sample 2 minus 1, and that'd be 44 plus 49, which is going to be 93. It's the same thing as saying, well, how many total people do I have in the entire study? And subtract 2 from that. So the degrees of freedom, the total degrees of freedom for an independent samples t-test are actually n minus 2. We had not seen that before because we've only ever up to this point used one sample of people. And so now it's going to be n minus 2. So a little bit different here. You look up in a t-table, or I actually calculated using just a Googled online t-critical calculator, degrees of freedom of 93. It's a one-tailed test using an alpha level of 0.05, and we arrive at a t-critical value of 1.661. You'll find in your book that you get a little bit of a different t-critical value, because if you look in the back of your book at the t-table, it doesn't actually have a value for degrees of freedom of 93. The closest degrees of freedom is 120. So that's why you get a bit of a different number. Now, don't worry, on an exam or a quiz or something, I would provide these numbers for you, or I would have you look up values in the textbook, but values that are already in the table. So don't worry about that too much. So if we were to put this on a distribution, it's now a t-distribution of differences between means. That's differences between sample means, if we want to be even more specific. The distribution of means is getting a little bit more and more and more funny and complex in terms of its name over time as we use different types of testing. But anyways, our independent t-test value we calculated was 1.06. We compare that to the critical region, which is established by a cutoff of 1.661 for the t critical value, and we see that our independent t-test value does not fall in the critical region. It's below the t critical value. So what do? Well, that means we cannot reject the null hypothesis. Therefore, we retain the null hypothesis. We didn't prove it. We don't think it's true. We just don't have enough evidence to suggest that it's false. So we retain the null hypothesis and state that the mean psychic accuracy was not significantly higher than the mean non-psychic accuracy. Another way to say that is the difference between the sample means for psychics and non-psychics was not significantly different from 0. We saw that the psychics had an accuracy of 26%, the non-psychics had an accuracy of 25%. So you're like, well, that's 1. Those sample means of accuracy are different by 1% out of 100%, right? Well, that we're saying is not statistically significantly different from 0, or 26 is not statistically significantly different from 25 in terms of mean accuracies of these two samples. Now, if you're thinking about, well, this is a one-tailed test, so what if we were looking for the mean accuracy of psychics to actually be less than the mean accuracy of non-psychics? You would have to look at the actual means, and psychics got 26, which is higher than non-psychics at 25. It's just that it's not statistically significantly more. And so we're really talking about only part of the one-tailed hypothesis, null hypothesis, which is that they are not statistically significantly different. So in plain English, the psychics in our sample are not better than non-psychics at predicting suits of cards. So ultimately, it might be the case that these two groups actually come from the same population. In other words, a population of people whose accuracy for predicting cards is no better than chance. But of course, more testing is needed. We never actually prove the null true in research. And so you basically would just try to amass a lot of studies that would tell you ultimately, which way the evidence trends. T-tests everywhere. Absolutely. This is the third t-test that we've covered. It is the last of the 3 major t-tests that are talked about in statistics. They're all really useful. I would say definitely I use the independent samples t-test the most of any of those t-tests. So definitely worth knowing and hopefully going to be very useful to you later on in your careers. With that, everybody, have a good one. I'll see you in the next video.